Thank you. Hi, everybody. So I'm going to be talking about that mouthful today. But before I get into that and before I forget, let me give you some brief background on myself. As an ex-academic, I'm not very good at self-promotion, so I have to do this before I forget. So right now, I'm an independent data science consultant based in New York City. I work with companies as big as Fortune 500 companies down to pre-seed stage startups to design, build, and deploy machine learning systems. Before I became a consultant, I ran a team at Dia & Co., a women's clothing retailer, building out machine learning systems. And then prior to that, I was an actual scientist studying superconductors at Columbia, where I did my physics PhD. And so a bunch of what I'm going to talk about today is actually written about in more extensiveness on my website. And then you can also find me on Twitter. And actually a bunch of what I'm talking about today, I've built out some open source packages which you can find on GitHub. So what is model remodeling with modern deep learning frameworks? So a lot of you might have, let's say, custom libraries that you use for doing something that might be machine learning, or it might just be, let's say, computational modeling. It turns out that, I guess what I'm going to argue is that, one, you can there's a lot of these frameworks that you can actually think about them in a more conventional machine learning sense. So kind of think about your problem as though it is, let's say, a straightforward scikit-learn problem. As well, there's a lot of these custom packages that if we rewrite them using one of the modern deep learning frameworks, like let's say PyTorch or TensorFlow, there's a whole lot of benefits that we can get by refactoring this code. And so with apologies to Daft Punk, you can make your code simpler, faster, better, and let's say more extensible. So how can you make it simpler? First and foremost, you can write significantly less code because you can offload a lot of the custom code that you might have written to the deep learning framework. Everything can be faster, so it's super easy to parallelize your code, vectorize, and also throw your code onto a GPU with these frameworks. You can build better models, so you can design arbitrarily complex models, not the models that are, let's say, hard-coded into the library that you're using. This allows you to find better minima in your objective functions and models that generalize better to unseen data. And what all of this leads to is that it makes it easier to modify your code, which gives you the ability to iterate quicker and achieve more data-driven discoveries, which is why we're all in this room today. And what I'd like to stress is that while I'm going to be talking about using a deep learning framework, none of what I'm talking about actually requires you to do deep learning. If you want to write convolutional networks and things like that, that's fine. But I think by rethinking of your problem as a conventional machine learning problem and using a deep learning framework, we can kind of hack these systems to get a lot of benefits for ourselves without necessarily having to go down like the neural network route. So I'm sure that a lot of you are already familiar with machine learning. I've been in this room for the past 2 days, and I think a lot of speakers have assumed that people are comfortable with that. I do want to kind of quickly walk through the recipe, just because I'm going to be coming back to this a couple times during the talk. And so there's kind of 3 main steps to doing a machine learning problem. The first step is to define an objective function. So this is something that you want to maximize or minimize. So maybe you want to minimize cost or a loss, or maybe you want to maximize a probability. You then have to think of a model that you're going to use to be able to predict values. And then we want to optimize. And what optimization means is let's determine the best parameters for our model to maximize or minimize this objective function. And so very quickly, we're going to walk through the most basic machine learning example there is. I'm going to try to go through this quickly. But kind of there's 2 fundamental pieces, which any of you who are familiar with scikit-learn, you know that there's targets. These are things that you want to predict. So that's going to be the y right here. These are known values that you want to predict. And then we have inputs. So this is information that we know about the sample. And our goal is to find a function that maps these inputs to the outputs, because we want to be able to receive new inputs one day and predict what the output will be. And so y is typically a long vector, and x is a matrix where the columns are your features, and then each row is kind of a different sample that you're interested in. And our goal is to figure out a model to map these two to each other. And so how do we figure out that model? We can design an objective function to do that. And so here we're going to say, all right, let's take the difference between the target and the output of our model, and we're going to square it and sum it all up. And our goal is going to be to minimize this, so to minimize the squared difference. In a simple linear regression, our model is just going to be a vector of coefficients. And so we're going to have this vector w. These are unknown values. We're going to have the inputs to our model x. This is our design matrix or our feature matrix. And we're going to say that our prediction is if we multiply the coefficients by x. And our goal is to learn the best values for w. So how do we learn these? We have to optimize our objective function. And if you remember from calculus class, if you want to minimize, let's say, a function, you can take the derivative of it, set it equal to 0, and solve. In practice, we don't take the derivative with respect to all of the data. Instead, we might sample a batch of data, take the derivative, update our coefficients, and kind of do this in an iterative fashion. So this is called stochastic gradient descent. Okay. All that's out of the way. Remember, we have this ML recipe, and I want to kind of propose a remodeling recipe. And so the first step of the remodeling recipe is to kind of make sure that you can think of your problem as though it's a scikit-learn problem. So can you think of it as an X design matrix and Y target values? So kind of cast the model into that schema. Sometimes it doesn't seem like it's possible, but oftentimes you can kind of finagle things around and do it. The next step, which we're not going to run into until the very end of this talk, is to make sure that the model is solvable via stochastic gradient descent. Sometimes it's not. And then lastly, we're going to optimize this model. And in our case, we're going to use a deep learning framework. I'm going to talk about PyTorch today. There's lots of other ones. There's actually a talk about Chainer this afternoon in this room, if you'd like to check it out. And I'm going to talk about how to do this all through a couple different examples. So the first example is called matrix factorization, which is kind of this academic thing that lots of computer scientists like, but it's also in, like, let's say the last 10 or 20 years gotten popular in the data science world. So what is matrix factorization? Let's say we have a matrix with rows along here, and we have columns, and we have some values inside of the matrix, but let's say there's a lot of missing values. And our goal is to be able to figure out what those missing values should be, or what are kind of the most likely values for those missing ones. So why might you want to do this? Let's say you're Netflix 10 years ago, and you have a whole bunch of users as your rows, and you have a whole bunch of movies as your columns, and maybe all of the filled in values are the ratings that the users have given those movies. You might want to be able to figure out what would the user have rated that movie that they haven't watched yet. If you can do that, then you can recommend movies that they might rate highly. And so that's kind of classically how Netflix did this. So they don't do that anymore. The goal, again, is to be able to fill in these missing values. And so far, this doesn't necessarily look like a scikit-learn problem yet, but we'll turn it into one. And so matrix factorization gets its name by trying to decompose the matrix into factors. And so the way that this works here is that, let's imagine we have this matrix R on the right. We're going to make a guess that we can multiply two tiny matrices in order to produce the values on the right. And so those tiny matrices, the first one is A. What we're going to say is that every row of the original matrix gets its own row in A, and then we have a very short vector associated with each row of the original matrix, maybe like 20 dimensions long. And then we're also going to make an assumption that there's a matrix B where each column in the original matrix gets its own column in this tiny B matrix, and then it has a short number of rows, which is the same number of rows as there are columns in A. And we're going to make this assumption that if we pick a row and if we pick a column and we multiply them together, that's going to give us the value inside the matrix. So if you look up how to do this online and Google it, there's all of these terrifying terms that come up and make me want to go back and relearn linear algebra. But it turns out that if you kind of rethink of this all in the scikit-learn framework, it becomes a bit more mentally tractable. So let's go through the recipe. We're going to define an objective function. And kind of naively, what the objective function might look like is we have our original matrix, we have the rows I and the columns j, and then we have some function that's going to take in the row and column, and we want to minimize the difference between these. In code, you might write this as, the difference between the known values and the prediction, and then we square it and take the average. So this is PyTorch code below. It looks pretty similar to NumPy code. But remember, we want to cast this into the scikit-learn framework with x's and y's. And so thankfully here, it's not too bad to do that. Instead of iterating over rows and columns, we can just kind of flatten everything into a long y vector. And then remember, the only inputs to our model are what is the row and what is the column. And so we can just kind of concatenate these guys next to each other and form a feature matrix, which is just two columns which contains rows and columns. And so now we have kind of an objective function in terms of an x and a y. So the next step is to define our model. In PyTorch, kind of any model that you have, you want to create a class for it that inherits from this module function. And there's kind of two key pieces to this model. You need to have your free parameters that you're trying to learn. And then you need to say what happens when you put data into the model, like what's going to come out. And so the first step to define our free parameters, remember our free parameters are this a and this b that we think exist that we can multiply together to predict values. And thankfully the deep learning world has already created this concept of embedding layers where you kind of input, let's say, an index and then it'll give you back a vector. And so we can define two embedding layers for a and b in the initialization function, and these are instantiated with random values, and our goal is to learn the best values of them. The forward method, that defines what happens when we input data into the function, what should we get out. And so the input is our, you can kind of think of forward like your scikit-learn predict method. So we take an x as an argument, we unpack the i's and the j's, which are the rows and the column indices. We can index them into a and b, multiply them and sum, and so what this essentially gives us is a dot product. So now we have our model. Finally, we need to optimize it, and so typically this is the worst part of writing bespoke libraries, but in our case it's only a couple lines of code. So we have our model f, and we first have to pass in all of the free parameters of it into our optimization function. And so we're going to use stochastic gradient descent. We pass in all of the free parameters. And then what we do is we do this thing that's kind of called a training loop. So we iterate through our data. We kind of sample batches of it. We pass the data into our model, and we get out a prediction. We then calculate the loss, which is the difference between the prediction and the true values. And then these two pieces here are kind of crucial, and what I want to stress is amazing is that you can do this in 2 lines of code. The first step is this loss dot backward. What that's doing is it's actually calculating the derivative of this loss function. And so if you do this by hand, you have to do a whole bunch of nasty calculus. And in this case, we just call this method, and you don't have to know math. It's great. The next step is once we have this gradient, we now have to update our coefficients. And again, it's a whole bunch of math in here, but in our case, we just call a method and we get this all for free. And so that's all well and good, but you might be saying, there's other libraries that do this. We already have this already. But what I really want to stress is how easy it is now to modify things. So let's say you want to add some regularization. Maybe you want L2 or L1 regularization. Typically what you'd have to do is you'd have to go backwards and recalculate the derivative, recalculate the optimizer steps, and rewrite all of the code. In our case, all of this is already in the deep learning framework, so we can just add this in as a keyword argument. Let's say you want to use modern optimization methods like Atom or Attograd. All of these, make their ways into these libraries, and they're there for free. Typically, if you wanted to use Atom, you would have to recalculate the gradients and recalculate the optimization steps. Lastly, and probably most importantly, let's say you have a concept for a better model that you could use here. For example, let's say you're Netflix and you have certain users who are just really pessimistic and they kind of hate every movie that they watch. You might want to create an offset term for each user and for each movie. So maybe some movies are always rated highly and you want this offset term. With a couple lines of code, you can add this into your model, and you don't have to then go back through and recalculate all of the gradients to account for this. It's kind of whatever you think up, you can do. Let's say that you're a big company and you have lots of data, or you have a big data set in your lab, and let's say you want to parallelize it on the CPU. Typically, you'd have to, let's say, learn a little bit of C, figure out memory management, and try to parallelize things in Python. PyTorch actually has like a 10 or 15 line example in their documentation that shows you how to use their built-in multiprocessing library to parallelize model training on a CPU. But we also know that nobody does that anymore because everybody uses GPUs now. And so this is some CUDA code from the implicit library, which is a matrix factorization library by Ben Fredrickson. And he's gone through the thankless task of writing out a whole bunch of CUDA code to do matrix factorization. And I would argue that that's a pretty steep learning curve for most people. Thankfully, these deep learning frameworks were built with GPUs in mind from the ground up. And so it's a couple lines of code. You first check to see if there is a GPU available. You then throw your model onto the GPU. You throw your variables onto the GPU. And that's about it. And now you get at least an order of magnitude speed up. And kind of circling back to the original arguments, this is an entire matrix factorization library that fits onto a slide, and we can easily modify the whole thing. And so I'm all about writing fewer lines of code because that's less to maintain. And so the nice thing here is that these libraries are well tested. You can just kind of outsource all of that work to the maintainers, which we are very grateful for. But maybe that's too much work. Maybe you don't like having to maintain these training loops. And so there's this excellent library called Scorch, which marries scikit-learn and PyTorch. And there's actually a talk about it today at 4:30. And so what it does is it kind of abstracts away the entire training loop. And so we can get rid of everything over here. And instead, we just instantiate what is actually a scikit-learn estimator. And so what's great here is that you can take whatever PyTorch model you want, you can turn it into a scikit-learn estimator, and then you get all the benefits of scikit-learn. So you can run grid searches, you can calculate metrics that you're used to, you can do hyperparameter searches, et cetera. And it has your regular .fit and .predict methods. But the key here, again, is you have to think of your problem in terms of these x's and these y's, in terms of kind of a conventional supervised learning problem. That was kind of in the weeds, so let's maybe try to do some things that are a bit more visual and with less code. So next thing I'd like to talk about is time series forecasting. So when I first started trying to learn data science towards the end of my grad school career, there's kind of like two separate things. There was like scikit-learn and machine learning, and then there was time series. And I kind of had no idea how to combine them, and I remember researching time series, and they talk about all these terrifying things like stationarity and making sure that Gauss and Markov are happy with what you've done. And I always kind of wondered, how do I join the two? So, let's say, I want to predict sales each day next week, and let's say I have a weather forecast. How do I combine that? It always seemed like there was the time series, and then there's X and Y and supervised machine learning. And so in kind of my quest to figure this out, I did what I do where I just fall back on things that I'm comfortable with. And so I was like, all right, I know how scikit-learn works, and so maybe I can think of this like scikit-learn. And so I decided to do that, and it turns out this is actually how some time series forecasting works. You can turn your single time series into an X and a Y. where your x consists of previous values of the time series. So maybe we use the previous 5 values of the time series as our, quote, features into our model. And then the thing that we're predicting is the red point, which is the next value in our time series. And we can slide along and kind of create a whole bunch of these x's and then a whole bunch of y's. And if we stack all the x's on each other, we get a feature matrix. And if we stack all the y's on each other, we get target values. And then you can feed this into like a linear regression model and you can predict the next value. But some of you might be saying like, okay, like that, you know, technically that's an ARIMA model with just autoregressive terms. And you would be correct. One thing I would argue is that by turning this into x's and y's, you could throw this in a random forest or XGBoost if you wanted to. But like, perhaps that's still not so interesting. And so I guess what I think is more interesting is that with time, or with the deep learning frameworks, you can define whatever loss function you want. And so typically the way that time series forecasts work is that you train a model to predict the next value in the time series, and then if you want to generate a forecast, like let's say over the next 7 days, you do this thing called recursive forecasting. So maybe you predict the value for Sunday, and then you use the value of Sunday as your input data to then predict the value of Monday, and you kind of keep feeding your predictions back into your inputs. But that always struck me as weird. Like in machine learning, we want to directly optimize what we want. And if I really want to know what are the next 7 days of this time series, then I should be directly optimizing that, rather than training a model to predict the next value and then hoping that if I roll it forward, it'll work. And so the nice thing with deep learning frameworks is that you can directly optimize what you want. So I can turn my target into the next 5 values, let's say in the time series, and I will directly minimize an objective function that does this. And that ends up being fairly trivial to implement with Scorch. Another example of time series is cumulative forecasts. So maybe you want to predict total sales over every day next week. And I know that sales should increase, hopefully. And so I'm predicting some function that is necessarily monotonically increasing. And so one of the nice things here is that I can actually bake in this domain knowledge into the modeling process itself. So I can define a PyTorch model, and maybe I use the latest and greatest of convolutional models to predict some results. But I know that the output should be cumulative. And so if I want to, I can pass it through a rectified linear unit and make sure that all the predictions are positive, and then I take the cumulative sum. And I don't know how to do the math to like auto-differentiate that myself, but we can just pass that into PyTorch and it'll do it for us. Okay, I have very little time, but I'm going to quickly go through this. So last example I want to talk about is a thing called ordinal regression. And so this is when you're predicting classes that have an ordinal relationship to each other. So let's say that you're predicting what size drink somebody's going to order at a fast food restaurant. And let's say you have small, medium, and large. We know that small should be closer to medium than it is to large. And so that's kind of an ordinal relationship. And so this is really, we have some domain knowledge and we want to use that in our prediction. So again, we have to define our objective function. I'll admit it's a pretty nasty objective function for this, but kind of anything that you can represent in math, you can represent in PyTorch or NumPy. And I have a library that does this if you're interested. And this is where we kind of get to that thing that I teased at the beginning, which is making sure that your model is solvable via stochastic gradient descent. So when we predict these classes, we actually have these free parameters called cut points that separate the classes. And we want to make sure that our cut points are in a certain order that keeps small, medium, and big in the correct order. And so we need these cut points to be ordered, but this actually turns out to be a constrained optimization problem, which doesn't lend itself very well to stochastic gradient descent. However, we can kind of hack this with these things called callbacks in Scorch, and we can say that every time we finish an optimization step, we're going to go back in and make sure that our cut points haven't switched places and that they're still in ascending order. And we can kind of hack this and still stay with our Scorch code, and it all works fine. So with that, I'd just like to end and kind of have you all think about if your problem could be cast as a machine learning problem, and if so, could it benefit from kind of all of these modern techniques? Do you have large data that didn't work with these bespoke libraries that maybe you could use here? And lastly, I've written about all of this on my blog, and I have some open source libraries that implement a bunch of this stuff in either PyTorch or kind of creating scikit-learn estimators to do these things. Thank you.
Questions?
Yeah, thanks. Hi, thank you. That was interesting. Going back to the time series modeling stuff. So I know that some of the deep learning frameworks have built-in. Well, I mean, some of the deep learning popular techniques like RNNs are like latent state that's auto-regressive in a sense. Have you had experience and could speak a little how easy it would be to just take a simple moving average time series model and use like a RNN with a small state, a small number of parameters to do that kind of model?
Yeah, so I don't think that would be too bad to do like in one of these deep learning frameworks. They tend to have classes for doing this. I guess what I've been more interested in is being able to do everything as though it's in scikit-learn, because the things that RNNs scare me about is that they're kind of these generative models in a sense, and I like the idea of just taking in the data and feeding it in and then making a prediction. But either one works. Yeah.
Anyone else?
Hello, great talk. We have a time series kind of question for you. We're analyzing time series, but we're not instead of forecasting future features, we're kind of putting them into a class, so A or B. Right now, what I'm doing is exactly what you did, fall back on what I know. I kind of just set y equal to our two classes. Is that kind of a valid method going forward?
Yeah. It totally is. So what you can do is if you have a historical time series, and I guess are you trying to classify points in the time series as belonging to different classes?
Yeah, just 50 rows in a time series, does that belong to class A or class B?
Yeah. And so one of the nice things here is that you can create, let's say, a regular time series model to, let's say, predict next values if you want, but you can also pass that through a logistic function if you want to be able to map it to a classification problem.
Okay.
Yeah.
Awesome. Thank you.
Thanks. This is maybe even too simple of an API question, but I was interested in this direct prediction versus recursive prediction in time series. If you wrap that up in Scorch or some other technique, how do you get multi-target prediction? You know, I want to predict 1 day and 2 day and 3 day and 4 day at the same time, but I mean, if that's a, big 4-dimensional space, that's a lot of its classification. If I sort of want 4 regressions, but what's the API for addressing that?
Yeah, so it actually works out of the box in Scorch, because basically your target, your Y, is going to be number of rows is the number of samples that you have, and then the number of columns is the number of forecast days that you care about. So maybe if it's the next 5 days, it'll be 5 columns there. And Scorch is set up to actually, I think by default, to receive 2D matrices as the target values. And in this scenario, you're just minimizing let's say the squared difference between the predictions and then those target values. And so it kind of just falls right out. I don't know if that made sense.
So basically, you do the predict and you get a 2D array out.
Yeah, you're predicting a vector, I guess. And the nice thing here is that you're using one model to predict all of those values. Kind of another way that you could do this is you could train a separate model for every day that you're trying to predict. But then you have to do a lot of training. Yeah.
All right, we've got about 1 more minute if we want any more questions. No? All right. Thank you so much, Ethan.
Thank you.